Hola, good morning to everybody. I'm very glad to introduce here Professor Massimo Della Valle, that is our guest for the next 2 months here at IAA. Massimo got his master's degree in Padua and his PhD in Armenia, where he also developed a very good, where he also started to become a very good chess player. So if you are interested to play chess with him, he's a very strong player. After the PhD, he spent some time at CSIC in Trieste, then he got a fellowship at ISO, where he was for 4 years, and he also got a very good capacity to get time, and for this reason, get time at telescope. For this reason, he got el apellido de El Tiburón. And at ISO, he also joined the group of Sol Perlmutter, and indeed he published the first paper. He was co-author with Sol Perlmutter of the first paper about supernova and AS cosmological probes. After ISO, he spent some time at Space Telescope in 2001, and then at ISO, but this time in Germany. And after all this time, he came back to Italy, in Florence, and after the position in Florence, he moved to the most beautiful city in the world, where he also was the director of the Observatory of Naples for 8 years. The research activity of Massimo spanned several fields in astrophysics of transient. He's a very good expert on supernova, gamma ray bursts, and also novae. And he also works on distance scale, and in particular, recently he also joined the group of the Cipher Smart about that is called PESTO, and also the group of that now is called Gravita, that is dedicated to the observational optical counterpart of gravitational wave events. Today, Massimo will talk about the empirical grounds of supernova GRB connection. So,
okay, thank you. And thanks to the director and the kind invitation to Cristina, Antonio, Alexander, and Luca for inviting me to work with them here. The last time I was here was about 10 years ago, and I was visiting our dear friend Xavier Gorosabel. Today I will talk about a series of issues. I have dedicated 2 slides to the supernova taxonomy to refresh people that maybe are not familiar with this business. Then I go through the GRB supernova properties, progenitor mass, GRB and supernova rates, and finally the conclusion. Well, finally, and then conclusion. Finally, I have some open issues that will take about 40% of my presentation. Okay? Let's start with the supernova taxonomy. The supernova classification is a spectroscopic classification based on the old paper by Minkowski in 1949. And he divided supernovae in 2 classes. Type 1 is that there is no hydrogen in the spectra. Type 2 is there is hydrogen in the spectra. Today, this original classification is much more complicated. There is a large variety of subclasses. However, we can still keep the original classification in 2 classes, calling the type 1a thermonuclear supernovae that come from the disruption of a white dwarf in a binary system that could be merging with another white dwarf or accreting material from a low mass main sequence star, so basically a cataclysmic system. And these are the supernovae that we use for cosmology purposes. And the other one, all the others are core collapse supernovae. And what we are going to talk today is a tiny subclass of this 1C that we call hypernovae or gamma ray burst supernovae. GRB supernova properties. Today we know about 50 association between supernova and gamma ray burst. But 90% that we know about this association is based on these 8 objects. That because they are nearby, so they can be investigated in deep details. First important point, the classification, the spectroscopic classification of these gamma ray burst supernovae the lack of hydrogen and helium in the ejecta clearly pointed out that these are Taiwan Sea. Then there are, these spectra are characterized by very broad features. And for comparison, I put here the spectra of a typical core collapse, a standard core collapse supernova type 2 plateau, and you see that the emission lines are actually much more narrow than here. And these imply large expansion velocity of the order of 30,000 kilometers per second instead of about 10,000 kilometers per second. The kinetic energy associated to the jet of the supernova, so not to the relativistic jets, is of the order of 10 to the 52 erg. And this is an incredible amount of energy, about 10 times the energy that is associated with a standard core collapse supernova. The range of luminosity is also pretty broad. You see we have faint object associated with gamma ray burst, but also bright supernovae, as bright, almost as bright as Taiwanese supernovae. That means that a large amount of nickel is synthesized in the core of the progenitor. And finally, the explosions are spherical. And this is a particularly important issue that I will going to make in a while. But first, I want to go back to this. Because now, you see, in the previous slide, I show you the main properties of gamma ray burst supernova in about 60 seconds, maybe 90 seconds. Every single item that I pointed out before took to the community months or years of tough work. And to give you the feeling of this, I used this, the issue of the classification. Look at what we read in '98 by Alex Filipenko. People that don't know Alex, he is the guru of supernova spectroscopic classification. And he wrote, the spectrum, talking about 98 BW, does not match any of the known spectral classes. So can you figure out the emotion that we were feeling when we understood that we were dealing with a completely new class of events, astrophysical events. And consider that 3 months later, this supernova was classified, I mean 98 BW, as a 1B. Then in July, Kay and Filipenko has a type peculiar 1C. Confirmed by Nando Patate, Antonello Piemonte in September, and we are already about 5 months later. The issue was still in progress. Then they go back, and in July '99, more than 1 year later, Nando Patate et al. Is a 1B. They change their mind. And finally, in 2001, after 3 years, the conclusion was similar to other type 1bc and type 2b supernovae. This gives you two clear indications. First, the whole process to achieve the classification of this supernova associated with gamma ray burst took 3 years for the prototype. And the second is a clear lesson of Italian lifestyle. Basically, you see, we agree on everything and to everyone. Okay. Now, let's go back to the last point, the asphericity in the explosion. If we model the explosion of a 98 BW by assuming a spherical ejection, you find about 30 times 10 to the 51 erg. associated with the ejecta. And this is an incredible amount of energy. It's about 30 times the kinetic energy associated with the 87A. Now, thanks to the papers of the Nomoto group, they introduced the concept of a spherical emission, and so the quest for energy can be decreased up to 70%. However, 10 times 87A is still an incredible amount of energy. And this concept is supported on empirical grounds by the study of the profile of oxygen and iron during the nebular stages of supernovae. When a supernova explodes, goes into a so-called homologous expansion, in which the velocity, expansion velocity, is proportional to the radius. So basically, the external layers move faster than the inner layers. So in a spherical model, there is no way to observe the profile of ions broader than the profile of oxygen, as it has been observed. So the only way to explain this is that this is not going to happen, but most nickel has been ejected along a preferential direction that in that case is, let's say, coincided with the line of sight. And this conclusion was strengthened in a nice paper that we have published in 2009 with Stefan Taubenberger, and based on 98 spectra, and which are connected with 39 objects, and we found that more than 50% of them are produced in a spherical explosion. The second piece of evidence for claiming that these supernovae associated with gamma ray bursts are strongly asymmetric when they explode is based on polarization measurements. There is a paper, 2001, by Wang et al., well, that is based admittedly on not on a large number of objects. So let's say that they show the tendency of 1C supernovae to exhibit a degree of polarization, and the polarization is a signature of a symmetric expansion of the order 4% that correspond to a ratio between the major and minor axis of the order of 0.2. So minor over a major axis. And here, 1% correspond basically to spherical emission. It would be nice to now to do again this paper to try to confirm, to verify this result, because this really was based on a scanty sample of objects, and so from a statistical point of view is not very robust. Progenitor mass. Well, the computation of progenitor mass justify the incredible amount of time, telescope time, that we devote for the spectroscopic follow-up of supernovae. Basically, the theoreticians, for a given interval of mass of progenitor, compute synthetic spectra, and then they try to match the synthetic spectra with the observed one. And they do the same with the light curves, synthetic light curves that are compared with the bolometric light curve derived from observations. Of course, we cannot do this only with one spectra. We have to make this comparison along the whole evolution, from early stages to nebular stages. That's why we need to sample the supernova every week or month, or even more. And finally, when the match is good enough, we have the mass of the progenitor. Of course, this, and now again, I was talking to you about this in about 1 minute, but takes months to do it. And there is a degree of uncertainty that is still attached. Basically, you see, for 98 PW, we have estimates between 25 and 40 solar masses. So there is a considerable, a significant amount of uncertainty. However, we are in a position to say that the progenitor of supernovae associated with gamma ray burst are pretty massive stars. At least 20, 25 solar masses, probably between 30 and 40. What about distant gamma ray burst supernovae? Are they useful? It is still worth spending time to observe them? Well, my answer is yes, for the reason that will be apparent in a while. Of course, gamma ray bursts are a classical cosmological class of astrophysical objects. The median computed on the Swift burst is about 2.7 in terms of redshift. And how we are aware that a supernova is emerging, or better, is associated with a gamma ray burst at a high redshift. When monitoring the decay of the afterglow, at a certain point, given point, you see that the supernova is getting over, is outshining the afterglow, and it appears like a bump. In some cases like this, we don't see any bump. What does it mean? Well, this is consistent with the fact that I showed at the beginning. One of the properties of the light curves, one of the properties of the supernovae associated with gamma ray burst is to exhibit a broad range in luminosity at maximum. So it could be there are gamma ray bursts associated with very faint supernovae, and we don't see them to appear to outshining the afterglow. In some cases, in a few cases, we were able to get a spectrum of the bump. And every time we do that, there are clear signatures of a supernova. So no doubt that the bump that I've showed to you a while ago, they derive from supernovae. This is an important paper by Kelly et al. That I'm going to explain immediately. Look at the Y, fraction of supernovae or long duration gamma ray burst. And here in the x-axis, there is the fraction of the light of the host. Take up, for example, the blue track, type 2. You see the 50% of type 2 supernovae track about 45%, about 50% of the light of the host galaxy. And this is is something that we expect. Take Taiwan A, the red. 50% of Taiwan A track about 45% again of the host of the galaxy, and that's fine. Look at what happened with long duration gamma ray burst, the black. 50% of long duration gamma ray burst track almost 90% of the light of the host. What does it mean that? This one, the gamma ray burst erupt in the brightest region of their host. And this why? Because the progenitor of long duration gamma ray burst are so massive, so their lifetime is so short that they don't have time to drift apart from the place where they were born. In other words, they are born and die in the same place, as it happens to many of us, by the way. But this is another issue. Taking advantage of this notion basically in the same year with a paper with Cody Raskin, Eva Scanapieco, and James Rhodes, we were making these theoretical tracks. This is for 50 solar masses. This is for 30 solar masses. These are the distribution of type 2 observed, type 2 supernova. The observed point, the track basically, the same, the 50% track about 45% of the light of the host. And you see that the data points of long duration gamma ray burst are in between the 50 solar masses track and 30 solar mass track. And this is in good agreement with the so-called direct estimates of the mass of the long duration gamma ray burst progenitors obtained through synthetic light curves and synthetic spectra. What are the gamma ray burst progenitor? We can answer to this question with thanks to this gamma ray burst 060218 associated with supernova 2006 EJ. This was a nearby object, so we could study it in great details. And these are the two plots, this one and the next one. This is the XRT light curves of this object, the black body, the power law, and this double bump is particularly interesting. Okay, this is simple to explain because that is a simple, the light curve of the supernova powered by the decay of nickel to cobalt to iron. This bump has been interpreted in 2006 as a shock breakout, signature of the shock breakout, when basically the blast wave intercept the pseudo-photosphere of the progenitor, or, as we think in this case, the dense wind due to the mass loss of the progenitor. And this black body, you see, is decreasing in temperature as is expanding. And when you compare the time with the radius, we found that everybody can find 30,000 kilometers per second, which is exactly what Nando Patata was measuring from the spectra. And so when you go back, extrapolate back here, you find 4 times 10 to 11 centimeter. And this, okay, red supergiant is 4 times 10 to the 13 centimeter. And this is a typical progenitor for a type 2 plateau, for example. 4 times 10 to the 12 centimeters is a blue supergiant and is the progenitor of 87A in the large supernova in the Large Magellanic Cloud. And 4 times 10 to 11 centimeters is the size of a Wolf-Rayet star. So the progenitor of this long duration gamma ray burst are massive and are Wolf-Rayet stars. GRB and supernova rates. Well, to compute this, we start from the two supernova survey that are the two pillars of our knowledge of supernova rates, the Asiago survey and the Lick survey. And we found a rate of 1 BC between 2.2 and 3 times 10 to the 4 Taiwan BC supernovae per gigaparsec cube per year. Then we have to compare this with the rate of long duration gamma ray burst. And well, you see, when you put together all this number, it comes out that this rate could be of the order, is an educated guess, basically this. 0.7 gamma ray burst per gigaparsec cube per year. And then, when you compare the GRB rate with the 1 BC rate, now we have to correct the GRB rate for the beaming factor. And there are a number of estimates of this. So basically, this ratio is between 1.5 and 0.02%. now you can ask, how robust is this number? And to answer to this, we have to find an independent way to measure this ratio. And this is offered by a paper in 2010, 2009, I can remember now, by Alicia Soderberg. She was monitoring in radio a number of 1BC supernovae, and they found a relativistic one, so an hypernova probably associated with gamma ray burst, but the satellite were watching some other sky area, so they didn't detect the gamma burst. But what has been observed later is very suggestive of the presence of an association between this supernova and the long duration gamma ray burst. So if you take this ratio at face value, 1 out of 146, it means that this ratio is of the order of 0.7%. That implies less than 4.5% at 99% confidence level, and 0.7 is pretty consistent with the previous measurement. There is also there is another way to measure the gamma ray burst. This is the gamma ray burst type 1BC supernova ratio. This is based on more on theory. Okay, this is the evolution of 1BC supernovae, the rate of 1BC supernovae with redshift computed with different star formation history. And this can be compared with the estimate of evolution of gamma ray long duration gamma ray burst rate with redshift by Vanderman, Puran, and Matsubayashi. And when you do this, you find a beaming angle of the order of between 10 and 30 degrees. So a simplified scheme for a gamma ray burst supernova event could be the following. This is an isotropic component which is carrying out most of the kinetic energy, 10 to the 52 erg, and mass, 510 solar masses, and is moving at 2,000, 3,000, 4,000 kilometers per second, or even more. And then there is a relativistic component that is that indicated with orange, highly collimated, moderately collimated component, 420 degree. The first one for high luminosity gamma ray burst, and the broader for low luminosity gamma ray burst, that's containing a tiny fraction of mass of the order 10 to minus 4 solar masses that is moving with Lorentz factor of the order of 100 of thousands. Now, if the line of sight is like this, probably, not probably, we miss the jets, and we observe only the hypernova. And when the line of sight is like this, we can observe the gamma ray burst and the supernova associated. Why I wrote here they simplified, because, for example, there are hypernovae which are not associated with the gamma ray burst. But this is a more specific issue, and I will not go into details. Conclusion. Observation revealed the existence of a continuum of properties among the different core collapse supernovae. Going from type 2 to gamma ray burst supernovae through this sequence of a spectroscopic type, we see that the mass of the progenitor is increasing, the mass of the envelope is dramatically decreasing, the polarization probably is increasing, and the rate is dramatically decreasing as well. The distribution of absolute magnitude maximum of 1BC compared with the distribution of hypernovae. Well, if you run a Kolmogorov-Smirnov test, you can just confirm what you can see even giving a simple glance to the plot. The two distributions are statistically indistinguishable. So now it could be interesting to understand the origin of the 5 magnitude dispersion in the absolute magnitude at maximum of these objects. Because we have a 5 magnitude dispersion for type 2, and we know why. That depends on the status of the envelope when the collapse of the core occurs. But here, there is not envelope of hydrogen or helium. So where does it come from, this? One possibility is that in case this dispersion due to the envelope, in this case, I don't say that it's completely due, but probably related to the asymmetry of the explosion. Of course, also the geometry of the explosion with the line of sight has a role. While the gamma budget covers several orders of magnitude, the luminosity of the gamma ray burst supernovae vary by a factor 4 or 5, so a couple of magnitude at the most. So basically, this fact provides evidence that there is no correlation between the prompt emission and the property of the supernova that are associated with long-duration gamma ray burst. Gamma ray bursts are very rare phenomena. We have seen that gamma ray burst over 1 BC the ratio is 1.5% at the most. The ratio between 1 BC and core collapse is 0.3, so that means that the gamma ray burst over core collapse is 5 times 10 to minus 3. Now, if you can take a salpeter function, initial mass function, and we consider the progenitor of gamma ray burst over the progenitor of core collapse, we found 0.15. That is about 30 times larger than this. So the question is this one. What causes some small fraction of core collapse supernovae to produce observable gamma ray burst, while the majority do not? Well, because we need a number of special conditions, because a massive star produces a long duration gamma ray burst. So first, okay, has to be massive. Then the hydrogen and helium envelopes have to be lost. Then low metallicity environment plays an important role. For example, take this plot. Who is the, sorry, I missed this. Okay. And this has been done with 53,000 galaxies observed with the Sloan. This is the plus minus 1 sigma, and this contour, the light gray, is plus minus 2 sigma. And you see that all objects related to long duration gamma ray burst occur in the region of low metallicity. The other point is binarity. We know that at least 70% of massive stars are in binary systems. And so now there is evidence for the observational evidence provided by Stephen Smart that many 1 BC supernovae are in binary systems. And then high rotation. High rotation is fundamental because this is the engine that powers the jet. So if you don't have angular moment, then to power the jet could be a problem. How much time I have? And one of this, and that's why Now, there is this strange, let's say, conundrum. On one side, you need high rotation to power the jet. On the other side, you see that these objects occur in low metallicity environment. Low metallicity doesn't favor the mass loss. And so, basically, we have to find a mechanism to avoid the supergiant phase. And that, of course, is when you have a huge envelope and a core, there is the magnetic, you see, the magnetic torque that decrease the momentum. When you lose material, when the progenitor, due to the wind, lose material, you lose momentum. And on the hand, you are left with a core that is not rotating or not fast enough to power the jet of gamma ray burst. So there was, in the last year, a number of models that avoid the supergiant, the red supergiant stage through completely mixing. So they are characterized by larger helium core that are still rotating fast. And finally, asymmetric explosion. Now we understand, or let's see, we have at least qualitatively, we understand why we can decrease this ratio by a factor of 30. Because we need massive stars, but also a number of simultaneous conditions have to be satisfied. And this probably is the reason for which from 0.15 we decrease this ratio up to 5 times 10 to the minus 3. Open issues. This is to beam or not to beam. Why? I was talking about jet connected with long duration gamma ray burst. I was telling them a problem with single massive star that are connected with low metallicity environment is that they have difficulties in losing the envelope and keeping a core rotating quickly. And but are we sure that all long duration gamma ray bursts are beamed? Well, the beaming at the beginning was a need, because with the fluence of the order of 10 to minus 7, 10 to minus 5 erg per centimeter square, distance up to 10, redshift of 10, energy in the produced energy in the hypothesis of 4 pi emission is sometimes 10 to the 54 erg. That have to be dissipated in about 20, 30 seconds. And 10 to the 54 erg is the rest energy of a solar mass in 20, 30 seconds. So when James Rose in 97, 99 had this idea that maybe the long duration gamma ray bursts are beamed, and the signature of a beaming can be detected during the decay of the afterglow in terms of an achromatic break. People start to look for them, for this achromatic breaks. And sometimes Some of them have been observed. By the way, this is a short gamma ray burst, but it is a nice example of a chromatic break. But sometimes we do not observe them. Sometimes there is no break. Sometimes there are breaks, but they are not achromatic at all. And then there is an important observation, and that in my opinion had important consequences on the gamma ray burst business. That is this gamma ray burst 130427A associated with supernova 2013 CQ, a gamma ray burst many people in the audience know very well because it has been extensively studied by Xu, Antonio, Cristina, and others. And look at the so-called amateur relation, that is a peak versus a ISO. These are all long-duration gamma ray bursts. And the gamma ray burst that I'm talking about occur here in the realm of a long duration, of a cosmological long duration gamma ray burst. But in fact, it was very close to us, 0.3 in terms of redshift. So it was possible to study, to monitor it very, very accurately. And okay, this is the relation. Okay, look at this paper by Max De Pasquale. He is monitoring this guy for at least about 3 years, and there is no evidence for any achromatic break or for any break. And now, due to the previous relation, that relate the jet with the time, Max told me that this exclude that this GRB was beamed by an angle that was smaller than 40 degrees, 40. What does it mean this? That, for example, if I take a long duration gamma ray burst, the Amati relation for long duration gamma ray burst. Here I set the maximum rotational energy for a neutron star, proton neutron star. That is about 3-4 times 10 to the 52 erg. Then, for example, I apply the distribution of a beaming angle found by Giancarlo Ghirlanda in 2013. I apply to all of this way. What happened? That they move clearly below this threshold. So that's fine. We can explain the part of them with the collapser, with the spin down of a neutron star, so with the magnetar, that's perfect. And what about the faint tail? Well, we have a number of possibilities: shock breakout, fake jet, minor bodies onto neutron star, or the merging of a helium onto a neutron star, as been proposed here some years ago by Cristina and collaborators. But what happened to GRB 130427A with at least 40-degree beaming? It moves just a little bit. So it's still, so this is a really challenge to the magnetar model. That's why in the last year with Maurice Van Putten, I proposed that for some hyper-energetic events that cannot be powered by the supernova or by the spin down of a proto-neutron star, maybe this can be powered by the transfer of angular momentum from a Kerr black hole to the envelope. And that was, for example, the case, one possibility, that was our interpretation of Assassin -15L, with an enormous energy in the light curve and in the kinetic of the, let's call supernova, but I have still some doubt that that was a supernova indeed. And this is the reason for which we believe that the Kerr black hole, the transfer of angular momentum from the Kerr black hole to the envelope was a good representation of the data points. Look, these are the data points that we took from the original paper by Dong et al. On Science in 2016. This is the track of the spin down of a magnetar, and this is the track of the black hole transfer, momentum transfer. So it's pretty good. Of course, we are aware that there is another interesting possibility, that this transient was indeed due to a tidal disruption on a Kerr black hole at the center of the galaxy. The lightning without thunder, GRB 060614. This was a long duration gamma ray burst, you see, was classified as long duration gamma ray burst, 100 seconds. So we were ready with VLT at the time to monitor this guy and to waiting for the emerging supernova. So basically we should have observed something like this. If the supernova was 98 BW like here. But you see, we didn't observe nothing. And that's, at the beginning we were really disappointed. Then we realized that maybe it was still more interesting, because you were expecting something and it didn't happen. So a number of incredible explanations were coming out. There are scenarios without supernova. So the supernova model, the supernova occurs months, years before the gamma ray burst, so we couldn't have observed. The transition neutron star to quark star, so the supernova is not expected. And binary merging is similar to what we observe. Now we can speak like this, what we can observe for short gamma ray burst. Recently I've read another one about the white hole. Are you aware about this? No. Okay, I will save you from that. But it was incredible, incredible. To me, the most probably the most interesting alternative, the most interesting explanation for 0614 without supernova, the scenario, without supernova, is the interpretation of this event as a kilonova. And this was provided by, this is Gene Zipping, so it is Gene et al., 2015, this is the first name. They base this conclusion on the unexpected excess in near infrared that has been observed for this gamma ray burst. And so they derive a kilonova rate from this event of the order of 16.3 event per gigaparsec cube per year. This is important because recently we have derived a rate of kilonova based on the big event of the last August, and we found 252 event per gigaparsec cube per year. And so it would be very strange that two events two similar events have so different rates of occurrence. So I cannot exclude that this is a kilonova, but as far as I can tell you, if these events are kilonovae, something is getting wrong between the rates of the 0614 events and the last August kilonova event. Scenario with supernova. Well, if a supernova is there, it should be like this. Very, very faint. Now the question is, do exist supernovae, core collapse supernovae, so faint? The answer is yes. There are a family of hyper-faint supernovae. Look at this guy, is a minus 12.5, that are really faint. So in principle, they can be accommodated inside the limits of the uncertainty and the optical observations of 0614. The point is that all these faint supernovae are of the wrong type, because they are type 2 with hydrogen. But fortunately, a few years ago, Valenti and collaborators found a supernova of 1b that was really, really faint, 2008 HA. And this is the first faint hydrogen poor low energy core collapse supernova. And this is very close to the luminosity that we need to accommodate this supernova as a progenitor of 0614 without changing the light curve that we have really observed. And the idea is that GRB 0614 is a massive star characterized by a small explosion energy, a strong binding energy. So most of the nickel that is produced in the core of the progenitor cannot be ejected. Is not in the ejector, but fall back inside the newborn black hole. So if in the ejector we have 10 to minus 4, 10 to minus 5 solar masses of nickel, basically we are observing a dark supernova. This is a possibility. The extreme case is that there is no supernova at all, but the progenitor fails to explode a supernova and it collapses directly into a black hole. And this idea justifies the searches that has been carried out recently, and maybe there is a candidate. This object that you see has disappeared suddenly, and between 2007 and 2015, this area were monitored with a good sampling, and there was no evidence for any supernova inside. So this is another possibility that we have to keep in mind. Outliers. Okay, go back to the amateur relation. One of the things that was disturbing many of us was that the prototype of the connection between 980425 and supernova 98 BW, so the prototype, of the supernova GRB connection, was an outlier of this relation that is that stands for long duration gamma ray burst. Well, recently in a paper with a student, Martone and Luca, we were able to show that probably the position of 980425 is due to an observational bias. For example, take 060218, the classical gamma ray burst associated with 2006 J, the one that I show that we have used to infer that the progenitor was a Wolf-Rayet star. When we have observed this with Swift, is perfectly matching the Amati relation. If we would have observed it with Fermi, that was also perfectly matching. With integral, started to move a little bit up. And then, if we have observed that with Bazzi, was completely outside the relation. And this probably because we are missing with the detectors that have been used to observe 980425, the faint soft X-ray tail. And the same has been the same kind of argument stands for 1612-19b that has been observed by Batt here, Fermi, and you see Peppo Sachs would have observed it outside the Trixim relation, Bazzi, and integral. So basically, I was telling you this story to tell you, look, if you now type in Google GRB 980425 and off-axis, you find about 9,000 results. And they mostly deal with models in which they explain the position of this gamma ray burst in the epic isoplane through off-axis jet model. Very likely we don't need any more of them because there are good reasons to think that the position of this gamma ray burst here is due to an observational bias. I have only one more slide, the larger variety. This is another big question. What produced the observed variety in long duration gamma ray burst phenomenology? We have a high luminosity gamma ray burst associated with bright 1bc supernovae. Low luminosity gamma ray burst with bright 1bc, low luminosity with faint 1bc, hypernova without gamma ray burst without a bright supernova or with a dark supernova, so I mean the direct collapse into black hole. Gamma ray burst from a standard 1bc supernova, there are two cases at least. Very long duration gamma ray burst, a new class of long duration gamma ray burst, longer than 10,000 seconds. This was longer than 25, for example, 25,000. With bright 1bc, and this was a new entry, very long duration gamma ray burst associated with the superluminous supernova. Hydrogen deficient, but was not a 1bc, was a superluminous. So a different class of supernovae. Now, I don't know how to answer this. I have some idea, but probably this instrument that has been, the last week has been selected by ESA among with the other two for phase A, and if it will fly in 2030, maybe this mission can help to answer all the previous questions, all the previous open issues. If someone is interested, go on AstroPH and look for Theseus mission, and if some of you want to join the crew, of course, is welcome. Grazie.
Okay. Thanks, Massimo, for the talk. Any question for Massimo?
Thank you very much for the nice talk. I wonder whether the common envelope evolution, the spiraling of a neutron star in the atmosphere of a massive star, has been considered in any of these models as producing this kind of gamma ray bursts. I have not seen these in your considerations, it should be not the thermonuclear runaway of in the surface of a white dwarf, would not be core collapse in a massive stars, but just a neutron star as a result of non-conservative mass transfer in binary evolution, giving this common envelope evolution, so-called common envelope evolution, spiraling of the neutron star and the collision of the neutron star with the core of the massive star.
I'm not sure to go to your question, but it seems to me more related to short duration gamma ray burst, to what you say.
I don't know.
Yes, no. I think it's. So maybe I should. I didn't tell to you at the beginning that I was talking about only the long duration gamma ray bursts that are associated with supernovae, because for short duration gamma ray burst there was so many ideas starting from the middle of 80 that these are due to the merging of neutron stars, or are related, however, to the merging. But then, the last August, we have basically the final proof with the detection of a system. There was a short gamma ray burst, gravitational wave emission, and finally also we detected the optical electromagnetic counterpart. I think it is more related to that. And so, yes, probably the mechanism that you were mentioning are at work. If I remember well, in the paper of helium plus neutron star merging, in your paper you mentioned the common envelope stage. So, yes, it's possible, but I think it's more related to short. Short. Yeah.
Okay, any other question for Massimo?
Okay, thank you for your talk. One of my question is about the paper that you have about 100, more or less 100 gamma ray bursts with about 40 spectra. 4 spectra, something like that. I suppose that you have different spectral or different not line oxide, but about different directions in order to see the sphericity or something like that. How much, if this is possible to estimate that, how much mass is involved in the asphericity? In other words, okay, you are considering that there is some kind of isotropy, anisotropy in the explosion of the material, and the material is already moving with different velocity in different directions. But how much mass is involved in this anisotropy?
Wait a minute. We are talking about 1 BC supernovae. So, probably we are here in this. The envelope of hydrogen on the top of this, between type 2b and 1b, probably is of the order of 10 to minus 1, 10 to minus 3 solar masses. This, as far as concerns the envelope. Then, as concerned, let's say, the main bulk, there could be some solar masses ejected. But when I was showing to you before the mass of a progenitor, for example, 25 solar masses, that is the mass of the progenitor of the main sequence. But then there is all the evolution, so loss of mass of the envelope through the wind. So when the core, when occurred the collapse of the core, the mass of a star is considerably smaller, not anymore 25 or 30 solar masses. Could be 10 solar masses, 8 solar masses. Basically, you are almost left with a core plus a small envelope or not at all envelope. So a few fraction of solar masses if you refer to the envelope, and 3, 4 solar masses, 5 solar masses if you consider the main bulk.
So you have also momentum anisotropy, not only velocity anisotropy. That is my question.
Yes. In the present, in the current scenario, the momentum of the core is the engine to feed.
Not the angular momentum, the linear momentum. My question is, all right, okay, you are spelling gas material, you know, with different velocities, but already you are spelling a mass ray also in different directions, a different mass ray in different directions. If you multiply this mass ray by the velocity, you have a momentum ray. Okay, the momentum ray is anisotropic too? Or you consider that you have different velocity, but more or less the amount of gas in all the direction is actually the same?
I don't expect a strong difference, very strong. I mean, a factor 2 or 3 of difference in velocity according to the different duration, not an order of magnitude. Okay, so if I'm along the preferential direction in which the nickel has been ejected, and I'm lucky enough to be, my line of sight is along that, and I measure 30,000 kilometers per second, I don't expect the other side of a star is moving at 3,000, no. Okay, it's moving 10,000, 12,000, 50,000, okay.
And the last question is about the error bar of the polarization you had there.
Shooting the red crocs. Come on, yes, I told you this is an interesting paper because in 2001 I found it as a nice suggestion, but it's based, as I told to you, really on a small number of objects which suggest this tendency. It would be very nice to repeat this paper, this exercise, because now we discover about 2, 3 supernovae per day, not 1 per month as during the Ziki time. Thank you to you.
Thank you. Very nice talk. This is very short. Besides the relation with metallicity with the mass loss rate, besides the relation between metallicity and mass loss rate that we know this is one of the vectors in this business, the point is, apart of that, what is what, in your opinion, the main reason, or why the RGBs prefer always low metallicity locations? Besides that, there is other evolutionary aspects.
Low metallicity favor the creation of massive stars, and we need a massive progenitor. I didn't show a slide that can, maybe I was wrong in don't do this, because this clarify my idea on this point that you were pointing out. You know, the basic model is the collapsor. To me, is a little bit paradoxical, because the progenitor are Wolf-Rayet stars. They have lost the envelope, hydrogen and helium, during this stage of wind. Okay. So we need a low metallicity environment to have massive stars. On the other hand, the low metallicity doesn't favor the loss of the envelope. And if you lost the envelope, because you need to do it, because we observe 1C supernova, so no hydrogen, no helium, this implies a loss of angular momentum. But angular momentum is what we need to feed the jet. So do you understand that we are moving here? At this point, this could be another exercise that we can try to make. Low metallicity environments produce stars with more massive helium core. Higher angular momentum, keep in mind the models of Young and Langer, which avoid the red supergiant stage, and therefore more energetic JRB events. At this point, we should find a relation between the metallicity and some of the explosive properties of gamma ray burst. This attempt was done in 2010, but
this is for single stars.
Okay.
My point was that you need
we agree. The other point is that without binary, the binary vector is very difficult, isn't it? Because binarity has the advantage that can strip the envelope without going through all these problems. I agree. Evolutionary models for World star at very low rates. World star for single star evolutionary models are low metallicity. This is well known, but my point now is why you don't find this kind of things, RGBs in, let's say, M82 type stars. So big star bursts where we know they are very massive stars, but they are not low metallicity or not low metallicity. So they are very big star bursts somewhere, sometimes, that they are not that very low metallicity. That's very massive, very strong ones, but they are not that low metallicity. Should we find some in these places or not? Look, I can only tell you that we start from observation, and we observe this in low metallicity environment. This is my starting point. Then I agree with you, and I was trying to stress during my talk, the binarity is a key ingredient. Look at has produced this binary-driven hypernova that is a model. I don't know if it's right or wrong, but has the merit to introduce the binarity in the business, because all of this are singles. And as you see, the single stars, for reasons that you were pointing out as well, have a problem, a serious problem. So the only things that we can say, if we put together observation, which say that these long-duration gamma ray bursts occur in low metallicity environment, but we need to strip off the envelope. But don't lose angular momentum. That's one possible explanation, very plausible, is the binarity. Yeah.
I think it's too late for other questions. If you're interested to make other questions to Massimo, he will stay here for another 2 months. He stays in the office of Cristina, the first floor, building C. So thanks again for this nice talk.